All right, ladies and gentlemen, I guess we are live. So we're going to start this nomenclature unit off with ionic nomenclature. So first things first, we got to learn a little bit about what nomenclature is in general. Nomenclature is a fancy science name for a system of naming. Yes, we even have a system for how to name things. And here in general chemistry, we're going to cover ionic and covalent and a couple of subsets of ionic bonding, being transition metals and acids. They follow similar rules, so basically all you need to really understand is ionic and covalent, and you'll be good to go in general chemistry here. But to understand ionic nomenclature and covalent nomenclature, you got to understand what's happening. So let's start with ionic nomenclature. Ionic nomenclature is when you have a metal and a non-metal interacting where they're donating their electrons. Ionic nomenclature is a donation of electrons. So this is when your metal throws off an electron, donating it to that non-metal. So once you donate that electron, you become more positive, and once you accept that electron, you become more negative. So let's take, for example, a very common species we know as table salt. So exotic, right? So I'm going to very quickly here draw the Lewis dot structures for table salt. These dots we know come from the valence electrons, and we know sodium has 1 valence electron, chlorine has 7. And all we're going to do is now we're going to see how these things fit together like a puzzle. So in reality, what will happen is chlorine will spin around or sodium will spin around because this is happening in space. So we can dip and dodge and wiggle and jive. All we need to line up and overlap in that spot. But that's not exactly applicable to do on a flat piece of paper. Doing this on paper isn't exactly easy. So how we do it on paper is we show the movement of electrons with arrows. So let's say I want to move this one over here to make that bond. Because the metal, sodium, will always give up that electron, or in most cases, will give up that electron. And chlorine, being the nonmetal, wants to make its octet. It wants to have 8 valence electrons, so it's strong enough to pull off the electron from sodium and maintain an octet within that bond. But now, after we've donated that electron, sodium is now short an electron, making it more positive, and chlorine has gained an extra one, making it more negative. And what do negative and positive things love to do? They come together. They make very, very strong bonds that are attracted to each other through something called electrostatics, where positive and negatively charged things interact and are held together. Now, I've kind of given it away that sodium chloride is ionic bonds. That is ionic, but let's slide over here. Not ionic. I don't know what that is. Let's fix that. All right. Now let's look at H2O. I know sodium chloride, NaCl, is a metal and a non-metal because sodium here is on the left-hand side of the staircase. Sodium here is on the left-hand side of the staircase. Anything to the left is a metal, and there sits sodium squarely right there. Now chlorine is another notable difference over here. Oh, no, not that. Blue. Chlorine's another notable non-metal because chlorine is squarely over here on the right-hand side. Now let's look at H2O. H2O, however, we know hydrogen to be a very special case where hydrogen is a very reactive non-metal. So since it's very reactive with 1 valence electron, it's over here in 1A, but we know it to be a non-metal. So I have here a non-metal, 2 of them precisely, and an oxygen. oxygen is right over here in the non-metal sector of the periodic table. So I have two nonmetals bonded together. Two nonmetals bonded together, well, that is squarely covalent, meaning these share electrons. Covalent things share electrons, and this sharing gives us shape. It gives us polarity. It gives us an end. And we'll learn about that as we go on further into bonding. Here we're just learning to label and classify as ionic or covalent. So here we gotta see our parts and pieces. So step 1, easy breezy, just split it in half. I see a Ba and an S. I know Ba sits right over here on the left-hand side of the periodic table. And then I know S sits over here on the non-metal side. So I have a metal and a non-metal, a metal and a non-metal. That would make me ionic. And the same deal over here with AlCl3. What I see here is Al is a metal because it's that metalloid exception on the staircase. So where it's technically touching the staircase, but we know it to be a metal because aluminum foil is a metal. And it's this exception to my staircase rule. And we see chlorine. Chlorine sits squarely over on the non-metal side. So a metal plus a non-metal makes that ionic. And this is just going back to us utilizing that periodic table to our benefit and getting things sorted and classified as ionic or covalent and then building its name from those conventions. And when we're talking about nomenclature, here in general chemistry, we have two main types, binary and ternary. Binary, you can think about two things. Like bipedal organisms have 2 feet. Binary nomenclature is dealing with 2 things. And ternary is 2 or more things. So it's usually got some polyatomics going on. Whereas binary nomenclature is just 2 simple things or an H in some non-metal, add IDE. And that's the general trend through all of nomenclature, particularly with ionic and covalent things. We're talking about that IDE ending lets us know we're in a bond and that we're doing things. Some notable exceptions to the rule here. Notable exceptions would be transition metals. These transition metals are a part of ionic nomenclature because they're a metal and something else interacting together. We still have to recognize that as ionic. However, due to the transition metals' electron orbital arrangements, they have a varying valency. This varying valency just kind of depends on who it's bonded with. So to be a good bonding buddy, you have to maintain this neutral outlook on life. So transition metals need some help to identify and signify what kind of state they're in based on who they're bonded with. And we do that through these Roman numerals. I have 1 through 10 listed here. Pretty rarely will you go to 10. Usually you'll stay squarely between like 1 and 6 with the oddball here and there. But it's always handy to know that an I is 1, 2 I's together is 2, then 3, then 4, all the way up to 10. If you need some help with Roman numerals, there's some great videos out there and articles you can look at to give you some help. But let's go on to how Roman numerals play into ionic nomenclature. So first things first, we start pretty simply. And start out here with binary ionic nomenclature. So here we have that metal. Anything on the left-hand side, like Beyonce said, this is anything on the left-hand side stays the same. Anything on the left stays the same. And the non-metal, anything on the right, you take the root of the non-metal name and then you add IDE. And the goal of doing all of this arranging and twisting is to maintain that octet, or those 8 valence electrons. If you have 8 valence electrons, you kind of have the configuration of a noble gas, and you're highly stable. And to sum up all of this blitter blather, we're going to talk about drop and swap. Drop and swap is when you just drop your charges based off your metal and non-metal and swap the numbers or the oxidation state we're given. And we know oxidation states are periodic information we can understand from our periodic table based on how many valence electrons we have to give off or have to take in to look like this noble gas configuration here. Notice how my noble gases have a 0 oxidation state. Oxidation state of 0 means you don't make any bonds because all of these guys right here are highly stable. Group 1A has 1 valence electrons to give off. We know they're metals. They tend to donate electrons, 1 of them precisely, so it can have a +1. 2A has a +2 arrangement. 3A has 3 to give off. Plus or minus 4, these are my special guys that have a varying type of bonding. Just depends on who they're with and how they balance out. And then after you get past carbon, then we come into the nitrogen family where I only need 3 more electrons to become 8 because I'm sitting squarely with 5 already. And then I only need 2 more to gain in with my oxygen family because I'm at -2 because I have 1 space, 2 space, and I'm looking like this. Then my halogens here, I only need to take in 1 extra one to look like them, so I'm having -1 charge. And when I say drop and swap, this information that charge, the plus or minus, goes away, and all we're dealing with are these oxidation numbers right here. Okay, this is down and dirty quick. And we know the arrangements for ionic nomenclature kind of follow the same suit we did up here with electrostatics, how this will whirl around and interact with an available bonding site on chlorine, but we can't exactly wiggle this around like we do on paper. So again, we show that donation of electrons through arrows. We show that donation through electrons through arrows. And that way we can see who's donating, who's receiving, and make things pretty clear on who's positive and who's negative. Since I gave off that electron, I take in an electron, I'm now positive and negatively vice versa. And I have that strong electrostatic attraction. Using this principle of drop and swap, we can start building formulas or moving from a name to a formula. It's pretty easy to do. You just have to slow down and take it one step at a time. So step 1, you ID your symbols and ensure it's ionic. Make sure what you're dealing with is ionic before you try to name it like an ionic compound. Number 2, you find your oxidation information straight off the periodic table. And number 3 is that drop and swap and quote-unquote reduce if possible. All of that blither blather can be summed up with just drop and swap. So let's get an example, because I feel like the best way to learn this is just to do it, and then you kind of catch on to the trend. So I see sodium chloride here. What I do is I split it down the middle, and I deal with one side at a time. Sodium's chemical symbol is Na. I get that straight off the periodic table. Chloride, chloro, that prefix chloro comes from chlorine at Cl. They kind of sound the same. Then I look at my periodic table and get some oxidation information. So I'm going to come back over here and look at these top information. I'm looking for my oxidation information for sodium. Sodium sits squarely in 1A, so it is +1. Chlorine sits squarely in 7A, so it has a -1. Positive and negative things attract. So you should always have a positive thing and a negative thing coming together. So now I've done this, check. I've done this, check. Now I drop and swap. I drop my charges, drop the charges, and I swap the numbers. So this one will come over here, and this one will come over here. So technically, what I'm now dealing with is Na1, Cl1, but we don't write ones conventionally because just a regular sodium atom in a formula already tells me I have at least one. For it to be there and represented with a symbol, I have to have at least one of them. So it's like writing 1, 1 twice. It's kind of redundant. So we simplify that down to NaCl. That's it. That's regular sodium chloride. Now what I like for you to do is hit pause for a second and try the rest of these on your own, and let's see how you go. Make sure you use your oxidation information from your periodic table. And let's see how we did. So magnesium chloride, I'm going to split this in half. Magnesium's chemical symbol is Mg. Chloride comes from chlorine, Cl. I know magnesium sits in 2A, so that's +2. Chloride sits in 7A, that's -1. I drop my charges and swap my numbers. Drop and swap. So this Mg keeps that 1 from chlorine, but chlorine now gets that 2 from magnesium. Nothing to reduce here, MgCl2. Now it looks like something a little more crazy. Strontium phosphide. Strontium's chemical symbol is Sr. Let me get not an eraser. There we go. Strontium's chemical symbol is Sr. Phosphide, phospho, that prefix comes from phosphorus. And phosphorus is in 5A. And its chemical symbol is P. Oh, nope, 2. All right. Strontium's chemical symbol is Sr with an oxidation state of +2 because it's in 2A. We know phosphide comes from phosphorus within 5A, so that's -3. I drop the charges, drop my plus or minuses, and I swap the numbers. Sr3, P2. And those don't reduce either. Capiche? So far, it's pretty easy. Now let's get a little more interesting here. I'm gonna move this one up a little bit so we can have a little bit more room. Now let's do lithium bromide since it's right here. Split it in half. You're dealing with one side at a time. Narrow the field, as it were. Lithium's chemical symbol is Li. Bromide comes from bromine. Lithium sits in 1A, so it's +1. Bromine sits in 7A, so it's -1. We drop our charges and swap the numbers, leaving us with LiBr. Remember, we have those 1s, but convention says we don't need them, so all we need to write is LiBr. Easy, breezy, beautiful. Same thing with these ones. Split them in half. Now, indium's chemical symbol is In. Iodide comes from iodine. In for indium comes from 5A, so it's likely a +3. Excuse me, 3A. I said 5A. It's definitely 3A. 3A. And iodine comes from 7A, and a -1. Drop those charges, swap those numbers, and you're in business. In gets that 1. Iodine gets that 3, but convention says we don't write 1, so it's I3. Indium iodide. And the same principle here, we got cesium sulfide. Cesium is squarely in 1A, so that's a +1. And sulfide is squarely in 6A, so that's a -2. Drop and swap and reduce if possible. So now we got CS2S1. Nothing to reduce here, so we leave it alone. Now, if you have something like 4 and 2, then we get into the whole idea of reduction. So then we would just simplify that down to 2 and 1 if it was 4 and 2. Use that comma denominator. And then you can get a little more spicy with your nomenclature as you move to a ternary situation. But moving backwards from names to formulas and formulas to names is a skill you have to do in this unit. So we got to make sure we can be able to identify an ionic compound from its formula to its name. But let's cover our spicy options with ternary stuff first, so that way we can cover it all at once. So all ternary ionic nomenclature means is that you're dealing with 2 or more things. Those more things being polyatomics. You have a list of them on your reference sheet, so make sure to use that to your advantage. And it helps if you have some memorized. So all a ternary ionic compound is you have your same situation as binary as before, but all we need to remember is that these polyatomics, everything on this list here, and this isn't exhaustive, I'm sure there's more out there, we just don't cover them here in general chemistry. These packages of polyatoms must stay together. So we use those parentheses to keep the polyatoms together, showing their uniqueness. And we have a special case where they don't end in IDE, and you hear everything else up here ending in IDE. You see the IDE ending here. That IDE ending lets you know, 1, you're in a bond, and 2, you're 2 individual elements. Here you have 2 or more, so then things get a little more less intuitive, I should say. So that way you must identify them as their polyatomic selves. So the process is the exact same. Split it. I'm gonna go ahead and split them all. Save myself some clicking. Now, magnesium's chemical symbol is Mg. Then I got this iodate thing. Iodate is weird, but it ends in ATE, so it probably tells me it's a polyatom. Polyatoms tend to end in ate and ite. So I see 8, so I'm going to come to my polyatomic list and look for iodate. Iodate is right here. Iodate's chemical formula is IO subscript 3. I know magnesium has a +2 charge since it's in 2A. Magnesium charge is +2, and then iodate's charge is given to me. Iodate's charge is given to me on my periodic table. That little minus sign right here, that little minus sign tells me that iodate has a -1 oxidation state. So I just put that in right above it. And then I drop my charges and swap my numbers, just like I normally would. But all right, I come to a little crossroads. If I just drop and swap like normal, MgIO3 2. Now I said I have 32 oxygens. That's not right. I have iodate. Iodate is IO3. So here's where the use of parentheses comes in to let you know you have 2 packages of iodate to balance out this formula. And the same process goes for the rest of them. So give it a try on your own, hit pause, go forth and prosper. And let's see how we did. So we got Mg for magnesium. I know magnesium to have a +2 oxidation state. I know from my polyatomic list that hydroxide is OH with a -1 oxidation state. I drop those charges and swap those numbers. I see, oh, that's not right. Like that. There we go. Mg1 from hydroxide, but I see 2 going to OH. I know I gotta keep it together, so I'm gonna run with my parentheses. Put things in a box to let you know we're done. And we're gonna give ourselves some more room here. Always less crowded. All right, lithium has the oxidation, a chemical symbol of Li. And acetate has a couple different forms. Acetate's condensed form is C2H3O2. Or if you decide to use the expanded one, CH3O. Live your best life. These are the same. I just like the condensed one because less writing. It makes things look less messy. And my periodic table says that lithium is a +1 oxidation state. Acetate is a -1. Drop in, swap, and reduced if possible, of course. Let's see. Drop it and swapping. Li1, C2H3O2, 1. Parentheses. Well, we don't need ones at all. So all we need is Li, C2H3O2. Beautiful. Now let's see, magnesium we just did is Mg with a +2. Phosphate, it ends in 8. It has that nice ATE ending, so I know it's a polyatom. I look over here to my polyatom list. Phosphate is PO4 with an oxidation state that we see right up here as -3. So we're just going to write -3 for our oxidation state. Drop those charges and swap those numbers. But now I got a 3 coming here to Mg and this 2 coming here to PO4. So I got to remember those parentheses, especially when we have more than one package of phosphate used to balance out that chemical formula. And the whole goal of this bonding is to maintain a 0 charge. That's why we're doing these bonds, to maintain a stable configuration. So if I know phosphate, if I know that one phosphate has a -3 charge, but how many of those do I have on my phosphate side? On my phosphate side, I have 2 of them. So overall, over here, I'm sitting at -6. All right. So let's just make sure we're neutral. I know one magnesium here has a charge of +2. But how many magnesiums do we have? We got that 3 magnesiums. So 3 times 2 is 6. So now +6 and -6 cancel each other out. And now we're stable. We're nice and stable together. And that's one way you can check yourself to make sure your formulas balance out and are 0. And now let's move from formulas to names, kind of reverse engineering your steps. So here you're going to be given a formula and you got to produce its name. The same exact process goes. You name the first name stays the same, so you name your first. Your last name comes from your second element. Your last name picks up an IDE ending, so that way you know it's in a bond. The only one you don't do that for are the ternary ones, the polyatomics. So if you see something in parentheses or you see 2 capital things next to each other, that's probably a good indication you're dealing with a polyatom. So let's see how it goes. Step 1, my first name stays the same. So I name my first. I got sodium here. Sodium is Na. And then my first name stays the same. My last name, I take the root. So F on my periodic table is fluorine. But I keep the root, so I keep fluoro. And then I change the ending to fluoride. Now it's sodium fluoride. Now, you've seen how it's done, so give it a pause and try it on your own. And let's see how we did. So first things first, I name my first one. Na is sodium. And then I got P here. P is phosphorus. I take the root of my second, phospho. And then add IDE as my ending. It looks something like this. It will look something like this. Now here's a special one. This is that ternary one. Same rules apply. Name the first, name the second. The first one is the special one, ammonium. Ammonium. PO4 is another one, ammonium phosphate. Because these both are both polyatoms bonded together in this situation. Now, will all of these happen in nature? Probably not. We're just getting some for example's sake here. But practice is always good practice. So here you have to recognize that these are both polyatoms. They don't get IDE endings. So they're special. They're special groups of elements. So that way we have to understand that and represent that properly in their name. So they keep their ATE ending. Because anything with "ide" usually comes off of the periodic table. Anything with "ide" ending is a straight element. If it's got that weird "ate" or "ite" ending, it's likely a polyatom. That's a good rule of thumb to check yourself by. Let's see how we did on this one. Ca, I named my first. That is calcium. And then As is arsenic. We take the root of the second, arsen. Add IDE, arsenide. Calcium arsenide. And that's how you undergo regular ionic nomenclature. You just put it together and drop and swap. It's easy as that. And the name of the game with this is practice. Practice, practice, and more practice, and more practice, and more practice, and more practice. Yes, we will do a lot of these examples and we will get through a lot of them. But this is so it becomes muscle memory to you and you do lots of this work in your head. When I say this work, I'm meaning the name the first, name the second, add IDE, split it in half, drop and swap, make sure it balances. All of that stuff will eventually become second nature to you and you don't have to continuously go back and check yourself. But while we're here, might as well enjoy the ride, so make sure to check yourself as you go. And if you have questions, you know how to reach out to me. I'm always available. Until next time.